Hello dear students, in the previous session, that is in the previous video, I have stated a theorem, that is a closed convex subset C of a Hilbert space H contains a unique vector of smallest norm. This is the theorem statement I have stated in the previous video. So let's prove this statement now. Okay. So here we have to take care of two things. One is the smallest norm, another is unique vector. We have two things, smallest norm and unique vector. So for that, first what I will do is I will consider one norm and I will prove that the considered norm is a smallest one. Okay. Since it is a smallest norm, I will denote it with infimum of norm x such that x belongs to C. So if there is an infimum means obviously there exists a limiting point. So from this, then there exists a sequence xn. There exists limit means obviously there exists a sequence which belongs to C such that limit n tends to infinity, norm xn is equal to A, right? That means this implies norm xn converges to point A as n tends to infinity. So now this is the sequence we have considered. We have to prove that the sequence which we considered is a Cauchy's sequence. Okay. I have to prove that this sequence is a Cauchy sequence. That means I have to prove that there exists limiting point there exists a limiting point, right? For that, what I will do is I will consider two elements or 2 points in this sequence, say xn and xm, which belongs to sequence xn. Since they have mentioned that C is a closed convex subset means we know that lambda x plus 1 minus lambda y belongs to C, right? Line joining segment. So if lambda is equal to 1 by 2, this will become x plus y by 2, which belongs to C. Using this, from a point, I can write this in terms of xn plus xm by 2, which belongs to C. Hence, from definition of A, that means from the value defining for A, I can write this as A is less than or equal to norm of xn plus xm by 2. Because we are defining A such a way that it is an infimum smaller value, right? So infimum of norm x where x belongs to C means this point will be greater than or equal to A. That is nothing but A is less than or equal to norm xn plus xm by 2. So using simple simplification, I can rewrite this as 2a is less than or equal to xn plus xm, norm xn plus xm. If you square on both sides, you will get 4a square is less than or equal to norm xn plus xm whole square. If you apply negative side to both sides, negative sign to both sides of your inequality, you will get minus of norm xn plus xm whole square is less than or equal to minus 4a square, right? So now let's use parallelogram law. From parallelogram law, what I have, norm xn plus xm whole square plus norm xn minus xm whole square is equal to 2 times of norm xn square plus norm xm square. This is from parallelogram law. So now I will use this law. You can write this equation as norm xn minus xm whole square is equal to minus, I am shifting this term to my right hand side. So xn plus xm whole square plus 2 times of norm xn square plus norm xm square. So this is from parallelogram law. Now we know what is norm xn plus xm whole square, right? So this term is less than or equal to minus 4a square, means whole term will also be less than or equal to minus 4a square. So this is nothing but norm xn minus xm square whole square is equal to, is less than or equal to minus 4a square plus 2 times of norm xn square plus norm xm square, right? So from the defined term we can write norm xn is equal to a and norm xm is equal to a. So this become as m and n tends to infinity, this will become norm xn minus xm whole square is less than or equal to minus 4a square plus 2 times of a square plus a square. From this you can write, isn't it? So now what will happen to your right hand side? Your right hand side will become 0. So norm xn minus xm whole square tends to 0 as m comma n tends to infinity. You can write this as limit m comma n tends to infinity, norm xn minus xm is equal to 0. So as m comma n tends to infinity, norm xn minus xm is equal to 0 means xn is my Cauchy sequence, right? Therefore sequence xn is a Cauchy's sequence. Next, what we have to prove? In statement they have given that H is a Hilbert space, right? That means H is complete. Also, and C is subset of H, that is convex, closed convex subset C of a Hilbert space H. So from this you can say that C is complete. C is complete means from the definition of complete space you can say that every Cauchy's sequence converges to some point or at some point in C, right? This is from the definition of complete space, at some point in C. So you can write that as xn converges to some point, say x0. This x0 belongs to C. Now norm x0 will be equal to norm limit xn as n tends to infinity, right? This is nothing but you can write this as limit into norm xn. So we know what is limit norm xn, this is nothing but a. So what you got? Norm x0 is equal to a. Initially what we have defined our norm. We are proving this norm is a smallest norm. So x0 is inside a means it is the smallest norm, right? Therefore x0 is a vector in C with the smallest norm A. So first part of the proof is over. The next part, what we supposed to prove? The vector we got, right? That is the unique vector. This is what we have to prove. To prove uniqueness, I will consider two vectors and I will say that these two vectors are equal. If these two vectors are equal means it's a unique vector, right? So uniqueness of x0. So let's consider two vectors, say x0 and y0 in C, such that norm x0 is equal to A and norm y0 is equal to A. Okay. So what we have to prove? We have to prove that x0 is equal to y0. They have given C is convex, right? If C is convex means you can write x0 plus y0 whole divided by 2 belongs to C. Again this term will be greater than or equal to A. So A is less than or equal to norm x0 plus y0 by 2. Correct? So again with a simple simplification you can write this as 4a square is less than or equal to norm x0 plus y0 whole square. Use parallelogram law. From parallelogram law I can write norm x0 whole square, norm x0 plus y0 whole square plus norm x0 minus y0 whole square is equal to 2 times of norm x0 square plus norm y0 square. So you can write this as norm x0 plus y0 whole square is equal to 4a square minus norm x0 minus y0 whole square. I am just shifting this down to this side. So this is a square, this is a square. 2 times of a square plus a square is nothing but 4a square. Okay. So now this will become norm x0 minus y0 whole square is less than or equal to 4a square. This is also 4a square. From this again just apply negative sign to both sides, you will get this. Okay. So this is 0, but we know that norm never take a value with negative sign. So norm x0 minus y0 whole square is always greater than or equal to 0. From these two you can write norm x0 minus y0 whole square is equal to 0. This implies x0 is equal to y0. Okay. So first I have considered smallest norm and I have proved that this is the smallest norm with a vector, and I have taken that vector and I have proved that that is the unique vector. This is all about this theorem. So now let's move to next theorem. The next theorem is, let M be a closed linear subspace of a Hilbert space H. Okay, M is a closed linear subspace of a Hilbert space H, and they have given that there is a point, say X, which is not in M but it is there in H. That means if this is my Hilbert space and this is some linear closed linear subspace M, I have a point X which is not in M but it is in H. Okay, let D be the distance from X to M. This is the point X, and inside M there we have considered one point. Let D be the distance from X to M. If this is the case, then there exists a vector y0 which is in M. We have to prove that there exists a vector y0 in M such that if you take norm of these two, that will be your distance D. This is what we are supposed to prove. That means first I have to show that there exists a vector y0 in M and this vector is unique. Okay. So to prove this, from distance, definition of distance, I will write the set as D is equal to D of X to M. Right, X to M is equal to infimum of norm X minus Y such that Y belongs to M. This is how I am defining the set. Okay. First, say again, there exists a sequence yn in M such that you can write that as x minus yn is equal to D. This tends to D. Okay, x minus yn tends to D. So let's consider two vectors, say yn and ym in sequence yn. First I will prove that this sequence is a Cauchy sequence. Okay, since M is linear subspace, we can write it as yn plus ym by 2, which belongs to M. Okay, so from the definition of D, you can write this as D is less than or equal to norm x minus. In this way I am defining x minus. In the place of y, I have yn plus ym by 2, yn plus ym by 2. So again do simplification, you will get 4d square is less than or equal to norm 2x minus yn plus ym whole square. So I can write this as norm x minus yn. You can split this 2x as x plus x. So x minus yn plus x minus ym whole square is greater than or equal to 4d square. Call this inequality as inequality 1. Use parallelogram law. So by parallelogram law, we can write norm x minus yn plus x minus ym whole square plus norm x minus yn minus x minus ym whole square will be equal to 2 times of norm x minus yn whole square plus norm x minus ym whole square. So using parallelogram law, you can write like this, right? So now since I have to prove that sequence yn is a Cauchy sequence, I will consider these two vectors. So I can write norm yn minus ym whole square will be equal to 4d square minus norm 2x minus yn plus yn plus xm. Sorry, this is ym whole square. Okay, so now as m comma n tends to infinity, you can write this as 2 into d square plus d square, which is nothing but 4d square, right? So 4d square minus norm 2x minus yn plus ym whole square. As m comma n tends to infinity, you will get norm yn minus ym whole square is equal to 4d square. We have seen that this whole term is greater than or equal to 4d square. So this is less than, since we have negative sign, it is less than or equal to, okay, minus 4d square. So these two gets cancelled, this will be equal to 0. Again norm never takes the value which is less than, but norm yn minus ym whole square is always greater than or equal to 0. From these two you can conclude that norm yn minus ym whole square is equal to 0. This is nothing but as tends to 0 as m comma n tends to infinity. So from this you can say that sequence yn is a Cauchy's sequence, right? Sequence yn is a Cauchy's sequence. So next what I have to prove, that I should say that there exists a vector y0 in M, right? So for that, in data they have given that being a closed subset of a complete space. Complete space means here it is a Hilbert space. So M is complete, right? M is complete means yn is a Cauchy sequence. There is a converging point, say y0 in M. So that means limit n tends to infinity yn is equal to y0, correct? So norm x minus y0 will be equal to norm x minus limit yn. You can write this as norm limit of x minus yn. So this is nothing but you can write this as limit into norm x minus yn. This is nothing but d. So from this you can say that y0 is a vector in M such that norm x minus y0 is equal to d. So this part of the proof is over. We have shown that y0 is a vector in M with norm x minus y0 is equal to d. Now I have to prove that this y0 is a unique vector. Again, for that what I will do, I will consider two vectors and I will prove that those two vectors are equal. Okay. So let y0 comma yn belongs to M. So I can write norm x minus yn is equal to d and norm x minus y0 is equal to d. Call this as equation number 2. So we have to prove that y1 is equal to y0. To prove y1 is equal to y0. So from the definition of d you can write d is less than or equal to x minus y0 plus y1 by 2. Do simplifications, you will get norm 2x minus y0 plus y1 whole square is greater than or equal to 4d square. Call this as inequality 3. So again use parallelogram law. From that you can write norm x minus y0. You can split this as x plus x plus x minus y1 whole square is plus norm x minus y0 minus x minus y1 whole square is equal to 2 times of norm x minus y0 whole square plus norm x minus y1 whole square. So this is d, this is d, so you will get 4d square by 2 from 2. Okay. So again I will consider norm y1 minus y0 whole square. So norm y1 minus y0 whole square will be equal to 4d square minus norm 2x minus y1 plus y0 whole square, right? So this is less than or equal to 4d square minus 4d square. This is equal to 0. So norm y1 minus y0 whole square is less than or equal to 0. But we know that this will not take a negative value. So norm y1 minus y0 whole square is always greater than or equal to 0. This implies y1 is equal to y0. So y0 is a unique vector. So first I have proved that there exists a vector y0 and I have shown that norm x minus y0 is equal to d. Then at the last part what we have proved that y0 is a unique vector. Okay. The next theorem is, if M is a proper closed subspace of a Hilbert space H, then there exists a vector z0 which is not equal to 0 and which is in Hilbert space H such that z0 is orthogonal to M. This is the statement of the theorem. So that means what we have to prove? First we have to show that z0 is orthogonal to M. Okay. For that, since they have given that, first I will consider the given data, that is M is a proper closed subspace of H. That means there exists a vector, say x, in Hilbert space H, but it is not inside M. So the point is inside Hilbert space, but it is not inside your proper closed subspace. Okay. So again, from the definition of distance from x to m, d will be equal to d of x comma m, which is equal to infimum of norm x minus y such that y belongs to m. Since m is proper closed subspace, that means if M is a proper closed subspace, then obviously there exists a unique vector from previous theorem, say y0, which is in M, such that norm x minus y0 is equal to d. This is from the previous theorem, right? Now I will consider one point, one vector, say z0, which is equal to norm x minus y0. X minus y0, where your x0 and y0 belongs to Hilbert space H. If these 2 points are inside Hilbert space, means obviously z0 is also inside your Hilbert space, right? So if you substitute these values here, you will get d is equal to norm z0. We have to prove that z0 is orthogonal to m, right? So we have a point, say we have a vector y inside m. So and I will consider a scalar alpha be some real number. Okay. Consider 2 vectors in M such a way that y0 plus alpha y is inside M. This is how I am defining my set, okay? That is proper subspace, proper closed subspace. So now you can write this as d square. From the definition of d, you can write this as d square is less than or equal to norm x minus y0 plus alpha y whole square, as z0 is equal to x minus y0. So substitute x is equal to z0 is equal to x minus y0 here. So this will become d square is less than or equal to norm z0 minus alpha y whole square. So you can write this as x minus y0, minus into plus, it is minus alpha y, right? So z0 minus alpha y. So from the definition of inner product, norm x square is equal to inner product of x comma x, right? So if you write in terms of inner product, this will become d square is less than or equal to inner product of z0 minus alpha y comma z0 minus alpha y. Okay, this will become inner product of, you can split this to 4 terms. So z0 comma z0 minus alpha y minus inner product of alpha y comma z0 minus alpha y is greater than or equal to d square. This implies inner product of z0 comma z0 minus z0 comma alpha y minus alpha y comma z0 plus inner product of alpha y comma alpha y is greater than or equal to d square. Again simplify this step, you will get norm z0 square, this is norm z0 square, minus alpha bar, I am taking this alpha outside, so it will become alpha conjugate into inner product of z0 comma y minus alpha into inner product of y comma z0 plus alpha into alpha conjugate into y comma y is greater than or equal to d square. So this is nothing but norm z0 square minus alpha into z0 comma y. Since alpha is real, alpha is equal to alpha bar. So I am just substituting that. Okay, alpha into inner product of z0 comma y minus alpha into inner product of y comma z naught plus alpha into alpha bar means it is all alpha square into norm y square, which is greater than or equal to d square. So norm z naught square minus alpha into inner product of z naught comma y minus alpha into inner product of y comma z naught plus alpha square into norm y square is greater than or equal to d square. From property of inner product, we know that inner product of y comma z naught is equal to inner product of z naught comma y whole conjugate, right? So just substitute this here. You will get norm z naught square minus alpha into inner product of z naught comma y minus alpha into inner product of z naught comma y whole bar plus alpha square into norm y square greater than or equal to d square. This will become norm z naught square. I will take minus alpha outside. You will get inner product of z naught comma y plus inner product of z naught comma y whole conjugate plus alpha square into norm y square, which is greater than or equal to d square. This is nothing but d square from the definition, okay, minus alpha into, here you will get real part as well as imaginary part. I will consider real part of this. So 2 into real part of inner product of z naught comma y plus alpha square into norm y square is greater than or equal to d square. Okay. So this implies minus 2 times of alpha into real part of inner product of z naught comma y plus alpha square into norm y square is greater than or equal to, I will send this term to my RHS part, so it will become 0. So this is nothing but, here if you consider the real part, so this is nothing but you will get a real part of z naught comma y is equal to 0, right? So since again if you consider the imaginary part, you have to replace y by iy. Replace